So, hello and welcome, everybody. I'm Jess Berg, and I'm the current chair of the Pacific Northwest AES section. I want to share that I'm based in Minneapolis and acknowledge there's a lot going on in the world. And I'm so grateful that we can gather in this way to be in community with each other and our shared love of audio. This is our section's sixth official meeting of the year, and we are so glad that you're here. We had a hybrid meeting in January at DigiPen Institute of Technology in Redmond, Washington, titled Audio Signals versus the Ear: Time, Frequency, and Bandwidth Revisited, presented by James J.J. Johnston. Thanks again to JJ for producing and hosting, to our treasurer, Lawrence Schwedler, for coordinating with DigiPen, and to Dan Mortensen and team for the technical support, our section secretary, Gary Louie, and our webmaster, Matthew Sutton. It was a very special evening for all who attended. A reminder that our section's meetings are typically September through June and will either be hybrid or fully online, so people can join and participate with us from wherever they are. Our next section meeting is being planned for March, time and date to be determined. Details to follow soon. The subject will be on open sound control, produced and hosted by Michael Ashton. And is Michael here yet, Dan? Do you see him on the list?
Seen him, no.
Okay. Michael should be joining us then at the second portion, and I'll have him share a bit more at that time. So stay tuned to the latest on our webpage, where you can also learn about becoming an AES member. There is a blue button at the bottom of the page that says Joining Info. You'll need references, and any of our sections committee members are happy to be your reference. Just ask. It is very important to our section that our meetings remain free and open to all. We use Zephy instead of Eventbrite because they don't take any fees. 106 people registered for today's meeting from all over the United States and the world. Donations totaled $85, which is very generous. For us, this covers all of our committee business needs, and we thank you. Today's meeting will begin with a tour and includes a brief intermission before the main presentation. We will leave the Zoom room open at the end of the meeting for anyone who wants to stick around for an after show hang and chat more about whatever audio topic you want. A friendly housekeeping reminder: we kindly ask everyone in Zoom to please use your real name first and last. Please reach out in the chat if you can't find where to do this, and we can assist you. Also, please be mindful of muting your microphone when not speaking. Please keep your microphone muted and your camera off during the main presentation as well. For Q&A, online folks, feel free to utilize the chat to drop questions in along the way, and I'll address as we can. In-person folks will have an audience mic to speak so everyone in Zoom can hear. We will pause along the way for questions, so we thank you for that. And I think this covers the business portion, so let's get to the fun stuff. We are very excited for tonight's presentation, produced by our Pacific Northwest Committee member, Luke Goodloomis. And I will now toss it over to Luke. Thank you.
With that, we will formally start the presentation. I'm going to hand this over to Denny McLane to introduce the Biamp team.
Greetings. Thank you, Luke.
You're welcome.
You did a good job.
Well, thanks.
Who taught you?
You?
Oh, that wasn't planned, but Luke and I have that kind of relationship. So thank you for coming. I'll introduce myself. I'm Denny McLane. I'm passionate about audio. There's someone on this panel doing a presentation tonight. His name is Deward Timothy, and in a rehearsal a couple of days ago, he says, I've got that disease called audio, and that is my bio. I have that disease. It's called passion about audio. And someone else who's passionate about audio is behind me. This is Todd Stevens. He's going to start us off. And Todd, take it away and introduce yourself.
Hey there. Thanks, everybody with AES for inviting us to host you and taking care of us. The support along the way has been much appreciated. And this is my first time actually addressing an AES crowd, except for like at trade shows when I was at Waves Audio. But I've been with Biamp since the community adoption. I was with Community Loudspeakers prior, and in 2019 became part of the team, along with the rest of the folks that we'll be talking with here in just a few. Just to, I guess, put some names on the folks who will be presenting today. We saw Charlie Hughes give a quick introduction, but we will see him in a little bit. Principal electroacoustic engineer with Biamp. We'll have John Loufik joining us. John Loufik is a long-standing member of our Loudspeaker Solutions Group engineering team, one of our senior apps engineers. We'll have Chris Barrow. He's our senior product manager for loudspeakers. And our friend Deward Timothy, the legendary audio designer and consultant, who I've just absolutely loved talking to over the last year and a half or so since I was introduced. Just a fine gentleman. So as you guys kind of got a glimpse of on the tour, you know that Biamp does lots and lots of technologies. But we're going to try to reduce that, well, we are going to reduce that to stuff that I really care about, loudspeakers and amps. I'm the director of the Loudspeaker Solutions Group on the sales front, so we're kind of a technical sales team. And I've got a small group of friends that supports me, but I think the most important thing is our lovely engineers with the group. So Loudspeaker Solutions Group, on the left are the design engineers that we have. Dave Howden, been with the company forever, oversees the crew. Rich Belando, John Loufik, who you'll see here, and Dale Shirk. You can recognize that they've all been with the company for a very, very long time. I'm actually still the newbie on the team when it comes to our Loudspeaker Solutions Group. Steve Goodwin and Mike Marr support our loudspeaker endeavors in the US, where our group overall is for the Americas. Let me move on here. So in terms of loudspeakers, just to kind of give a broad view of what we do, we cover lots and lots of verticals, right? So small systems, whether it's a conference room, multi-purpose room, all the way up to stadiums. We get involved in it all because we have lots of solutions out there. And Biamp is just putting fingers into lots of different categories. So while the collection of the Loudspeaker Solutions Group came from Community, we are Biamp, and we design all Biamp loudspeakers. Community is a brand under Biamp, so people often call us the Community team, but we are the Biamp Loudspeaker Solutions Group. And back in 2019, when we got adopted, was about the time LVH was seeing the light of day, and that's the puppy we're going to talk about today. So it's gone through a long history of development, and you've got the right people on the line today to discuss some of that journey. So I'm looking forward to kind of hearing it again from their perspective. So a very enjoyable group of people. That was one of the main reasons I really was proud to join Community back in the day, was because of the people. It's a good family. Just absolutely love these guys. Denny, you want to kind of convey some of your excitement behind what we've been doing with LVH?
What, me? Well, microphone, yeah. Thank you. Transducers, small ones at the beginning of the stage, big ones, bigger ones at the end of the stage. Fascinating area because it marries the two worlds that we live in, the electronic world in the middle, amplification, DSP, microphone preamps, and all of that fun stuff that does processing and shaping of the sound and so forth, tools that we use. And at the front end, small transducers. And this here is a beast. Yeah? Good word? Yeah. This is the manifold that is the magic inside here. This is what we're looking at here with 4 high-frequency compression
Do we
drivers
want to
mounted
go,
on the
sorry,
back.
do we want to go to the, not the screen share picture, but to the camera? So Todd, stop sharing your screen and we'll look at the camera. Go. Sorry, Denny.
No, thank you.
No, thank you. Are you horning in on my action? Horning in,
Taking a
sorry.
nap, man.
Luke, did you take note? All right, so then we have 4 high-frequency drivers mounted here on the backside. You can see them, 1, 2, 3, 4. The mid-range drivers, which are a derivative, if anybody knows, back in time to the M4, which was an amazing 4-inch mid-range driver. This is the M200. This is only the diaphragm. You can see the magnet structure on the back here. That is the mid-range driver. There are 2 on this side and 1 on the other side in the middle. And then we have 4 12-inch woofers. Very important that you understand, even though this was named the LVH large venue horn, take the large away, put it on the shelf. Take the L that could have meant loud, put it on the shelf. Today, I want you to think about, hang your hat on the realization that this is an amazing acoustic tool. Take a moment, put all the horsepower, and put it aside. It's useful. It is there when it's needed. But this is a tool of very accurate finesse, of acoustic energy that is controllable. It can solve problems in spaces where you can't solve problems any other way. The horsepower is not the issue here. It's available if you need it. So that is, you can come back and look at it later. There is some graphics the Zoom people will be able to see that will show this in a better way. But that is kind of the backstory there, the back of the cabinet taken off. And by the way, I will mention there are, even though I'm about to tell you that this is a point source speaker size in terms of its look and feel, it is also something that can be arrayed itself, but we're going to get back to that, and I don't want to confuse things, so let me stay on track here. So what you see now is so what I'm doing is I'm introducing some concepts that I feel are very important. We're going to get into I am not doing details here. This is just some broad stroke introductions. LVH is approximately 1 meter by 1 meter by about 1 meter deep. It is about the size and the impression of a point source speaker. What you have on the right there is a line array. A line array, a banana hang, if you will, is multiple cabinets that are able to achieve things that we've been doing this now for a while, but it's certainly a tool that achieves things in a way that is quite remarkable. What the LVH achieves is, on the right, coming out of a point source size box. We actually have the performance, the coverage, the asymmetrical beamforming that simulates what you see on the right. So when I was on stage and I could have maybe in a small room, I could have reached up and touched the bottom of a line array hang. A lot of times it's just too long to use that kind of technique because it's hanging into video projection in a church, environment, house of worship. It could be, high school auditoriums in a lot of places they're not spending the money to build the proscenium and the ceiling height to get the height. You just don't have the space to hang all that. Another thing that I learned from Deward Timothy is that when you do that, a lot of times you lose the ability to get a proper angle. Angles are important. A long J-hang of a line array, while that is very applicable in some situations, we sell a line array that's fantastic. It's called the IV6. However, when you don't have the space to hang that much cabinetry, and you want to get that angle so that it's hitting the audience area and not hitting the back wall, reflecting to the front of the stage, this is quite a remarkable tool. You're going to learn all about that when they talk about the science and I stop talking. The other part of this I wanted to cover is that a typical application for a point source is that you aim the center angle, the center directionality of the speaker at the back row, because you want to get that. Sometimes in some situations, sometimes it looks like a Christmas tree. You want to lay that Christmas tree down so it's going across the audience area and hitting energy as much as possible that's going to be as even as you can get out of a point source from the front to the back. But as you can see from the top view there, that's a ease focus file showing a typical point source. That technique only gets you so far. The energy, obviously, for those that are used to seeing these, the hotter colors are the higher SPLs. The cooler colors are the lower in volume SPLs. However, then you take the LVH, again, the same size as a point source speaker, 1 meter, and you have the ability to do beamforming. You see now we're aiming the center of that aim point of that speaker at the center of the audience area. So now we can take all that energy that is usually wasted, is usually floating off, what a term, right? But is going off into the areas of the room and bouncing around and creating reflections and so forth that you don't want. And it's also energy that is not directed at the audience. Now you're able to take your beam, your center point of aim, instead of hitting the back row, you're hitting the center of the audience area, and all of your energy is now in a perfect world, maybe a 3-to-1, 4-to-1, or a 5-to-1 ratio. Deward can speak to that later and explain what that's all about. I did miss something. I was about to ask you if I did, and I remembered. Please note in these two examples that the beamforming steerable LVH is also steering energy away from the stage area. So in the top view, you've got energy on the stage. That's not going to give you very much gain before feedback. And in the bottom view, as you can see, the cooler colors are on the stage and a tremendous amount of gain before feedback is achieved. With that.
Yeah, so looking at just kind of more of a specific application, this is just a modeling of a real church. Looks like my video may have gone away, but am I live on the far end is the question.
We see your room with the line array hanging.
Okay, all right. So this space could use a multitude of solutions. It's not the tallest room, but it still was able to accommodate a line array system. And here's the side shot of this. So the design was based kind of first maybe around a line array solution. So that's 5 boxes of our IV6. Obviously on the left, you've got your stage and then the audience floor and then a balcony in the back of the room. Well, that hang is starting to address or get in the way of sight lines. Even if it's getting close to, whether it's architectural features or displays, you start just getting distracted by the speaker, right? So you might just not have the real estate. You need to make sure sight lines are accommodated. So with an LVH, we've been able to replace those line array solutions with something that can equate to the coverage and the coherence across that audience plane out of a smaller device. And it's a 3-way device. Where maybe large format line arrays can go into the 3-way realm, but many are 2-way devices. But here in a compact device, we are working with a 3-way solution for capable of high output rock concert kind of experience. But kind of what we've been talking about is it's also just a problem solver. So acoustics will still govern a lot of solutions, and you'll just see more of what this brings to the table. But here's that room. The top is a top view of that space, the church. And then you've got the side view with a line array turned on right now. Now this line array is kind of cool because I don't know what the video is doing in the room. So I guess the far end is really enjoying my presentation.
You are.
So I'll have to just speak to
You
what...
guys can't see your PowerPoint?
Something happened to our wall here.
Oh, no.
Yeah, but, well, I got to just describe it and move on. You guys can catch it in the recording. Yeah. Where we have the 5-element solution from the IV6, these arrays, that 5-box solution can hang on 1 amp channel. We passively attenuate and gain shade on the back of the speaker. Looks really good covering the room. Can't you guys just tell it's amazing coverage, right? But the other solution being the LVH, now with custom beamforming from a smaller device, I can get actually better coverage, including up on the balcony. So the decision can now be made, do I want to put delay speakers up on the balcony, or can I get the whole room covered from the main PA and not include all of the commissioning requirements when you install those, the expense of it, you name it. There's a lot of reasons why eliminating a delay ring can be beneficial. And kind of what Denny was alluding to in an earlier picture, how we were avoiding the stage. Well, these frequency plots display just the evenness of coverage for one, but the bottom line that is not as even as you can see compared to the rest of the plots here is on stage. So with LVH, we're getting better rejection on the stage, important for gain before feedback. So again, obviously we can do much more to manipulate the directivity of this device, so it does become quite a problem solver in many, many cases. Short of any more pictures that we can't see here, well, you guys aren't going to see a video, but I have a question in the room.
Well, I'm thinking of the, I don't know, should I be speaking close to a microphone? Do you want to pause and take a minute and try to figure it out? Because we're kind of shortchanging the people in the room.
Yeah.
We can take a break here.
Well, we can take a question for sure. Okay. Yeah.
Regarding the houses of worship, as a recording person, I'm working in the so-called hearing that acoustics, which are
We don't have Luke's mic.
I would be curious as to how this deals with that circumstance. As I say, long reverberation times in a space that are quite prominent and actually desired by the music directors for the particular churches involved.
Yeah, and actually, I know we'll kind of develop this whole presentation into more of the attributes and the solutions or problem-solving abilities of this device. But when I can start really controlling that energy and start avoiding, say, the back wall, I was just in a church yesterday doing a demo, and it's amazing what that does to diminish intelligibility. So keeping as much energy, as large a bandwidth as I can off of those surfaces, that back wall is just an evil. Balcony faces, I can actually start splitting the beam on these things and avoid a balcony face. So it just maintains intelligibility. Obviously, the reverberant environment is best treated with treatment. If you need to calm the acoustics, we regularly have conversations with people that no matter what speaker system you put in this room, it's going to be the same reverberant experience. The best we can do is direct the energy where it should be, on the ears. Yeah, if the people actually tell us where the audience is, it's amazing. So that begins the benefits of this, right? If the larger bandwidth we can start controlling, the less we're exciting the room. Let's put the sound on the ears like we always aim to do. But yeah, high directivity and the ability to do custom beamforming that layers that coverage pattern onto the specific audience area. That's where we win. I guess, yeah, let's
let's do a couple minutes. We'll troubleshoot this,
right,
and then we'll have this and spin it around as a backup. And we're ready to roll, I think.
Yeah.
Hooray.
So we'll go ahead and move on. So before we get to the rest of the team here, I want to play a video. It's about 4 minutes, but it's a case study of our installation at Georgia Southern. It's about a 20,000 seat stadium. It was the first time we really deployed an asymmetric LVH solution, and Charlie Hughes presents this. He was on site. I say I was there, but I was kind of just hanging out behind him because I'm not the guru he is. But it was pretty fascinating commissioning experience, and he's going to speak to some of the difficulties we're up against when we were there. But it was all a happy ending. So, but it'll kind of show just what we were capable of doing in a large venue with this. Let me migrate over to that.
At the football stadium at Georgia Southern University, they needed a new sound system that had a lot better coverage in the seating areas that had higher SPL capability than their existing system. One of the biggest challenges the university had with their existing system was the crowd noise. The sound system couldn't get above the crowd noise, so the fans couldn't hear announcements that were being made. When they would try to push the sound system to get as loud as they needed it to, it suffered from a lot of distortion. When we arrived on site at the stadium, the loudspeaker arrays had been installed, they were wired to the amplifiers, and they were ready for testing. We did notice that it seemed the arrays were not aimed down quite as much as they should have been. We wanted to try to re-aim them slightly, but that just wasn't possible. The installation crew had done a great job of locking them in place, and there was no wiggle room to try to move them at all. Time was a critical factor in this job, as it is in most jobs, because the installation crew had to be at another stadium in a different state the following week. So commissioning had to be finished that week. The weekend after that was opening day, first game of the season, so there wasn't any time to spare. When we first listened to the right array covering one side of the stands, the coverage was not as even as we thought it should be. That was the first problem we encountered. Secondly, we noticed a very significant reflection off the press box. When we were walking the stadium listening, our beamforming guru, Shen Yu, noticed that some of the dimensions of the stadium itself didn't seem to match up with the dimensions in the Focus 3 model that she was using to create the beamforming FIR filters. We measured some of the aspects of the stadium itself and confirmed that there were errors in our Focus 3 model. So we updated the Focus 3 model to match what we really needed, and we noticed at that point that our target audience areas originally were about 20 feet higher than they should have been. For most installations, this would have been a very serious problem. Typical point source loudspeakers would have had to been re-aimed to hit the audience areas that were about 20 feet lower than in the original model. That would have required a very large, expensive crane to be brought in to drop the loudspeakers and re-aim them. The beamforming capabilities of LVH 900 allowed us to change the coverage pattern by supplying new beamforming FIR filters to the arrays. We updated our ease focus model with the correct dimensions. Once we did that, we had very good results, and it sounded very nice. We discovered there was a problem after we got the coverage corrected, and there was a significant reflection from the field house in the opposite end zone from the loudspeaker arrays. That created some serious distractions in some of the listening areas and intelligibility problems in others. We were able to adapt to this obstacle by using a feature in Focus 3 of avoidance zones. Shen created some of those in the model and then generated new FIR beamforming filters to reduce the reflection off the field house. This reduced the level of the reflection about 8 or 9 dB, which worked marvelously. Unfortunately, it also compromised some coverage in some of the farther seating areas of the stadium, decreasing that about 8 dB in SPL. So we knew we had to come up with a way to optimize between reducing the level of the reflection and reducing the level of the SPL in the curvature areas. Shen went to work again, resulting in a new set of FIR filters that brought the level of the reflection from the field house down about 6 dB. There was only about a 3 to 4 dB reduction in the SPL in the seating areas at the far end of the stadium, so we had a good compromise. After using Venue Polar and Fear Maker, sometimes there is some array EQ that's required to make things sound good. I had developed a lot of that before we got on site, but I wasn't sure how well it would match what we found in reality. It actually seemed to work out fairly good. When we did some listening and a few measurements, we decided that we needed to remove 2 of the EQ filters, covering the low mids, I believe. Once we did that, it really tightened up the sound and everybody was very pleased.
All right. So at this point, I'm going to transition over to Mr. Chris Barrow, if he is ready to go. He is our senior product manager. He was at the birth stages or gestation stages of LVH. Let's not get too weird here. Anyway, Chris, take it away.
Maybe all the above. Yeah, hi. How are you? I'm Chris Barrow. Like you said, product manager. Been with Community for just shy of 23 years now. Um, Developed products all my career and sort of got into it like a lot of people, being a musician and build amplifiers and that sort of thing when I was younger. Anyway, let's talk about LVH. They wanted me to talk a little bit about sort of how we got here. How did we get to this unique product? And really, a lot of it was just asking questions about what are people trying to do. And this is going back, I mean, at least 10 years. We started thinking about this. We stopped being a company that sold musical instrument store products, and we didn't sell products for touring anymore. We only did install speakers. So we started looking around the industry, going, well, what can we do different that other people aren't concentrating on? And we started looking at line arrays and large point sources for venues like stadiums and that sort of thing, and realized that people are trying to do things in these unique geometries that don't always work out the way you'd like. In a stadium like this, you have the three different geometries of these seating areas. If you're doing point source systems here, you have problems with seams between cabinets, and there's not really that much area for that in this type of application. But we also realized that if we're going to have a large speaker that has a lot of pattern control, so we can do stadiums, what other type of applications need that? Well, any large reverberant space, like a house of worship, like an auditorium. We learned this over the years from putting so many of our R2 loudspeakers in places like convention centers and auditoriums that are, infamously reverberant. So we wanted to make a product that not only was big and loud and could throw distances, but we needed to cover deep, narrow spaces, preferably from a single speaker if we could. And if we couldn't, how can we get more coverage? And how can we suit all different geometries, like a room that is shaped this size, or we're going to run into a bunch of different geometries. Every room, we don't get to pick the room. We have to make the sound fit the room. So what can we do to do that? Here are some of the applications where point source speakers are implemented, and sometimes it can work out, sometimes it can't. The image on the left, the three white speakers, that's two full range speakers with a subwoofer behind it. In that case, the top speaker and bottom speaker are pointing at two unique audience areas, but they have to be hung a certain distance apart because they just at the seam between the two speakers is just not coherent. There's of course a lot of comb filtering going on there. And on the right, we have an application where we're trying to cover a large curve at the top of the bowl. So those two speakers are aiming at one audience area, and unfortunately, you end up with some seats just don't get good signal. But both these applications, a lot of times now we'll see a line array involved, and that's great for if you're a professional sports stadium or a D1 college. Well, you look at the numbers, that's a very small part of the actual market out there. A lot of it is smaller fields, in smaller colleges and high schools, and also houses of worship, of course, is a number one. They tend to be reverberant. When we look at these speakers, we not only had to look at what are people trying to do and they can't do, but why can't they do it? And these are a lot of the competitors out there that are still out there today. And when you look at these, but there's really no way these type of point source speakers can ever array coherently. And we wanted to make a point source speaker that could array coherently. Now, why is that? Well, if you have a 30 or 40 degree trapezoid box, you really want the point a projection of your high and mid frequency really to be behind the box. And every one of these examples on the page, including our own R2s, the mids and highs are actually forward of the woofers. We're not really making a coherent point source behind the box to array two boxes. I mean, we have constant curvature systems now where you can put two 30-degree boxes together because they make a coherent point behind the box. That's sort of how we designed our IV6 line array, was using that sort of thinking. We have a 5-degree box that has a single point behind it at at where 5° would be, and the 15° box has a point behind it where all the drivers meet. Well, we could use that same concept to make a larger horn speaker. We can then array these point source speakers. I mean, why would we bother? Well, again, looking at some of the applications where line arrays are implemented and maybe shouldn't be, where you look at it and go, there's got to be a better way. On the right here, we have this short throw but wide seating area, and that is, I counted them, that's 10 line array boxes, and they've done it. They certainly don't need the SPL from that in this room. They're just trying to get this distance ratio from front to back covered and covered down low. And because of the low curvature of most line array boxes, 5, maybe 10 degrees most, they had to end up using 10 boxes to cover this room. And this room on the left, I'm actually going to blow this up so you can see it a little better. There's actually five cabinet line arrays going around the front top of this. The upper balcony is getting covered. The seats are getting covered. But you notice what's not getting covered at all are the front rows, where the people who need to hear the most, or maybe you're paying the most, aren't getting signal. A lot of front fill speakers on the front of this stage. They have a height problem here, and we'd like to cover the distance to the back of the room and these front seats all at the same time with one speaker, and have it sound nice and clear like a good point source should. That's what we developed with the LVH 900. Most of the time when you have a speaker that has high output, dispersion, you want dispersion control, you want low distortion and smooth frequency response, you kind of have to choose between which of these you want and which of them you're going to leave behind. We didn't just make a blowtorch. We made something that is actually very subtle, and the insides of that show it. This image on the right is looking at the face of the loudspeaker into the horn. The entire face of these loudspeakers are a horn. There's two, we'll see in a second, there's two different horizontal patterns. But for the single cabinet variant, we're doing up to 136 dB continuous SPL. And with their dual cabinet arrays that we were doing originally, we can get up to 140 dB with two cabinets. And that's with 50 hertz, 20 kilohertz range. But we're not just making just a point source here. We've made a device where we can actually do some steering. Before I get to that, we also have indoor and outdoor versions of this, of course, making it rugged enough to be outdoor, pretty enough to be indoor. I just did a whole video for that. That's up on our YouTube channel. It's a best 4 minutes of your life. You want to go look for it. Talking about how we do our outdoor loudspeakers. And of course, we designed this with all the bracketry like you would for an array. We have a U bracket if we're just using one cabinet, but we have line array like hanging grids, pullback bars, and splay brackets. We can splay the front, we can splay the back, depending on if we're trying to get a wider coverage or if we're trying to get more SPL to throw far. Very much like a line array. In a line array, you put a bunch of straight cabinets at the top to throw SPL to the back of the room, and you curve more toward the bottom. Well, we can simulate that sort of same response using just 2 or 3 boxes. We wanted to cover this type of application, which is sort of the slide we opened up with here, which is, we want just one box thrown at each area with absolutely no seams in between them. And we did this doing a couple of different things. This is an overhead view of the cabinet cut in half, showing our 60-degree horn, the woofers up front, the HFs in the back, and the mids right up there in front of the HFs, and then the 90-degree horns, everything shoved a little further forward. The 60-degree horn is really the most arrayable out of these. Here's what you guys are looking at on the stage if you're there live, which we lovingly call the engine block. That has our 4 HF drivers, our 3 mid-range drivers, and our 4 LFs. The mid-ranges and high-frequency drivers all come together on a manifold that's then joined to this large fiberglass horn. Now, the thing that's great about this is, if you look at it, the rear cover of this speaker is only a few inches behind those HF drivers. And the angle of that horn almost exactly matches the angle of the cabinet around it. The point for where those HF drivers meet as one is outside of the cabinet. It's behind the cabinet. And similar goes for the mid-range drivers. So we've done our best to get our physical product right before we even do any beam steering. Let's make the most arrayable point source we can. And because we know it's not going to be perfect, let's then apply some beam forming to it to make up the difference and make everything work perfectly. So, getting the 40-degree cabinet with a 40-degree angle horn and the HFs laid out so where they'll meet back at a point behind the cabinet is huge. Now you figure, hey man, how hard is that? Just slap a bunch of drivers onto a manifold and call it a day. Well, it turned out to be a little more difficult than that because of the way our engineering team approached it. So here's some slides from the patent that we applied for this manifold. And I should have explained what we're going to look at is this manifold on its side and standing up. So that's what the next image is. These are the 4 HF drivers in the back. You can see here that the path for the HF is pretty straightforward. There's 4 little hornlets for the HF. They do have flares in the end to minimize any acoustic impedance transitions from the stems to when it goes into the larger horn, minimize standing waves. That's all pretty straightforward, and you can see they're all splayed out at the angles. Then we got to the mid-range drivers. And these mid-range drivers are mounted on the 3 holes you can see in the center of this manifold. The paths here get a little more complicated because the mid drivers fire in from the side. Then we immediately turn them 90 degrees to go forward out of the horn. So all the mid-range energy comes out of these little slots on the front. Well, the energy also goes back down the horn, whether we want it to or not. And that really became a problem for us. Energy, you can see the arrows, the energy goes back down. Of course, it can come straight back out, reflect off of these again. And that gave us a problem where we had a notch at about 800 hertz. So here's another image from the patent illustrating what's going on if you can't picture it in your head. In the top image, our energy is coming out from these slots and heading both directions, out from the cabinet and back in. We're getting further away from the cabinet. We finally, at the bottom one, we finally get a reflection off that HF driver. It's now coming back out, delayed, but almost full strength at a good distance behind the energy that went originally straight forward. And that's where our 800 hertz notch came from, is having this big delay. So how do we resolve this issue? It's not exactly straightforward. What we had to do was basically make a leaky horn. We had to have somewhere for that mid-range energy to dissipate so it didn't reflect back. So what we're looking at here is, again, the side view on the top right, showing where the leaky slots are. On the bottom right is a look from underneath. You can see how narrow that is. And then on the left side here, we're looking at the slot, looking down the throat of the HF driver. So we put slots in there so that what happens is when the energy comes back down the throat, it goes through those slots and exits into the cavity of the cabinet. Well, if we just left those slots open, it didn't show enough impedance to the HF driver, and it didn't absorb enough of that rear energy. So one of the critical things we did was to find the right, acoustically resistant material to put in there. And I don't know if we disclose what that is in the patent, but it produces just enough impedance that it doesn't impede on the HF wave, and the mid-range energy gets absorbed. So here's the same drawing showing what's happening with the absorption. We leave the horn going 2 directions. We're now, when the energy is going back down the horn, we're starting to absorb when it's going down that direction. When it reflects, it's also getting absorbed, coming back out. We have a lot smaller signal following our main signal coming out the front of this horn. This is the main issue that we resolved with this, was how do we get our signals aligned the way we wanted to. The HFs are curved. The mid-ranges, as you saw in this, are also curved coming out of there. And this is the trade-off we had to make, is when we make a leaky resistant path, a leaky horn, we have to trade off something. We got rid of our reflection, but we did have to reduce some of the low frequency extension of the horn. And one of the great things about this M200 driver is it's about 100 dB, 110 dB sensitive at 1 meter, almost no matter if it has a horn or no horn. It gets loaded better or worse. And in this case, we were able to load it down to about 700-800 hertz, about 600-700 hertz, where it's perfect to cross over with the low frequency drivers. And and you can, and if it's not clear here, I mean, what we're looking at is the solid line is where our 800 hertz dip was before we put any leaky paths in the horn, and then this dashed line, we have a nice workable high pass going on in the mid range that's very workable to work with the low frequency driver. And then last but not least, these woofers also have cover slots on them, and that's not just as easy as throwing a cover slot on. Here we also had to balance, we had to make sure the cover slots were large enough that they didn't make noise, but they had to be small enough that they didn't interfere with the mid-frequency wavefront. And of course, we wanted to minimize the airspace between that cover and the woofer to get so we didn't have too much acoustic low passing going on, so we couldn't get up to the mid-range crossover point. And after we got all this acoustically figured out is when we started applying beam forming and beam steering. And I'm going to turn it over to John Loufik here, our applications person. So while I know how we dreamed this up and the problems we face doing it, John's the guy who's using this and applying it every day. So I'm going to let him explain to you where we went from here.
So our first stopping point, I guess I should introduce myself. My name's John Loufik, and I'm with Biamp. Was kind of mentioned earlier by Todd. I've been with Community beginning in 2006. Actually, next month is 20 years for me. And I work in the Loudspeaker Solutions group as an applications engineer. I've had a few different roles around the company related to that and product development. So this was a project where I was involved in the development part at this point in time. And our starting point was to be able to check the boxes for what I'll call nominal vertical patterns. So if you were to go back a dozen slides in your mind and remember some of these very common large format horn-loaded products that are in the market, all of them have nominal vertical patterns. So the LVH has a fixed horizontal pattern, but most horns obviously also have a fixed vertical pattern. And so the flexibility we developed here in the manifold by driving all of the drivers individually or in pairs is that we're able to manipulate the gain or the level and the phase or the delay on drivers and adjust what is the vertical pattern. So that was our starting point, so that we would have something that's spec equivalent to things that are common. For the occasions where spec equivalent is important, or you just want that as a starting point. It might be a little odd to start with a product that can do anything, right? But starting with something that's kind of familiar can be a good launching off point for a designer. So 3 patterns in a single cabinet were released 20, 40, and 60 degrees. The horn by itself, by the way, if you don't put anything on it but a crossover, is about 50, 55 degrees. So we're able to shrink that pattern or open it up a little bit. And then pairing up cabinets to do the arrayability that Chris was talking about earlier, we released 3 patterns there. A double cabinet 20 degrees, so for going further and getting louder. Think of that scoreboard system at the end of a stadium or something like that. And then an 80 and a 100 degree for occasions where you need a lot more vertical coverage. So this was great to have 6 patterns on both products. So the 906 60 degree wide horizontal has all these patterns, and so does the 909 90 degree. So you have a dozen patterns to pick from out of that's currently what's in the GLL. As you'll see, though, as we step forward here a little bit, that there's some limits to this in terms of actually getting ideal coverage. So on this next slide here, you'll see a set of
John,
drivers
sorry to
in
interrupt
section.
Can we're still seeing Chris's screen. You'll need to share so we can see your slides.
Yeah, he's going to push these 2 for me.
Oh, okay.
Yeah, we're good. Thank you. So on this diagram here, showing a 40 degree or any of the single cabinet vertical patterns, the way the nominal pattern is accomplished by providing the same DSP and amp connection to the first and the last high frequency driver. So the one at the top and the one at the bottom. They share a channel of signal processing and amplification. The inner pair, 2 and 3, they share a channel. And then the mids likewise have a symmetrical parallel connection. The mids first and last for 1 and 3, and then 2 is separate. And so this results in a symmetrical pattern vertically, but adjustable by applying different DSP settings inside the DSP amplifier that we run with these, and it results in the patterns. So changing your vertical pattern is just a matter of changing DSP settings. The next diagram shows the double cabinet variety. This is essentially the same thing, only stretch that out across 2 cabinets. The very top driver and the very lowest driver share a channel, and then progressively inward toward the center, they share DSP amplification channels to do essentially the same thing, but across the geometry of 2 cabinets. So the last thing I'm going to leave you with, and then we're going to hear from Deward about some of his experiences in the design world and where this seems to be a helpful feature. I'm going to do a comparison here, left and right, of a symmetrical pattern, that's the one on the left, and an asymmetrical pattern, or a steerable pattern, on the right side. So this is the same venue. We're going to see more of this venue later as a case study, but this is essentially what they have right now at this site, and they've had this for a few years, is the left system. So the symmetrical patterns were available, and 60 degrees vertical was a perfect fit to the seating. The horizontal on those cabinets is 90. So there's 2 of them, one for each half of this small church environment. But you can also see it's a little bit hotter in the front than in the back, and it doesn't quite get to the edges perfectly. We're actually relying a little bit on the reflected energy off the wall to support some of those seats. The STI scores in this room, the intelligibility scores, were 0.7 something in the middle, right on axis, and 0.6 right at the edge of the seats, and then it would drop to 0.5 at the wall. So it was extremely directional speaker in this room. And they wanted that to be able to get over some of the noise and reverberant problems in the space. On the right side, if we were to take the same product and do nothing but alter the wiring so that we can apply the DSP filters for an asymmetrical, steerable pattern, we can achieve more uniformity across the room, and we can tell it at the same time to avoid the back wall or to avoid the stage and try to narrow that coverage front to back. So that's where we're going, and the rest of this presentation will talk about this. And I'm going to hand this off now to Denny. So I think, Denny, you had an introduction for Deward, and Deward's going to talk about his experiences in the field and how this type of technology relates.
Thank you, John. Well, part of the reason we're all here tonight is because of a journey that started when Chris Barrow came out a year and a half ago to Salt Lake City, and we had visits to 5 different venues in the Salt Lake City area, high school auditoriums and such, and had conversations about our line array that then segued as Chris introduced us to what you are all hearing tonight. LVH, again, has been introduced for about 6 years, but in the symmetrical, very powerful way of doing things, but the almost a skunkworks operation was underway to do this magic called steerable LVH. So that was introduced in the conversation with Deward. We were dealing with conversations with him on his experience with different venue challenges. And that really was the start of what happened and what created this meeting tonight when I brought it to Luke for a certain application that he had that was extremely challenging. And here we are. But I would like to introduce Deward. I worked for many companies I worked for JBL Harmon 3 times, and during a 7-year run, I was introduced at the beginning of that run to Deward a long time ago. And when I came back and worked for Biamp, I was able to come back into the Salt Lake City area and sit down with Deward and reintroduce myself after being missing for a couple years. So it's been a pleasure to work with him. I personally knew quite a bit about him, but he's a very humble gentleman. And so I decided to call in, the heavy ammunition in terms of introducing him. So I called Brenda Brown and got some quotes I'd like to share with you about Deward from Pat Brown of Synergistic Audio Concepts Pro Audio Training. Deward holds more SynodCon, Synergistic Audio Concepts is what that is from, SynodCon seminar completion certificates than anyone on the planet, 38 in total. He has more practical real-world experience designing and tuning sound systems than nearly anyone in our industry, including too many projects in extremely challenging acoustic spaces. And you know how Pat, and it came from Don and Carolyn Davis in the beginning, it depends. Well, a quote that Pat uses in SynodCon training that he attributes to Deward is he's known for saying, equalization begins at the drawing board. Pat loves that quote and often uses it in the seminars. And beyond all of that, Deward is simply one of the most well-liked and highly respected designers in the field of professional audio. With that, I bring you Deward Timothy.
Well, thank you. I don't know that I deserve that, but I have been around a long time. That's one given thing. If I make it to October, it will be 60 years that I've been doing this sort of thing. I'm going to come at this from a little bit different angle. I've been on a crusade, I would say, for 35 years to get manufacturers to look at what they're building in a little different way, and have been very unsuccessful at it. And I have I have one particular room, and the reason why I picked this room is because it's had 4 sound systems in it, and I designed the last 3. Of course, being around for that long, you can imagine if they replace them every 20 years or so. And so what I'm going to do here is switch to a SketchUp drawing. Can we see that okay?
Yeah.
It's there.
Are you sharing from your computer?
Oh, wait, no, you're right. I'm a little nervous, so I neglected to do that.
No problem.
Okay, now you should be able to see it, right?
There you go.
Okay, so this is East High School Auditorium. We draw all our models in SketchUp because they're easily transferred to other platforms when we're trying to model coverage in a room. And like I said, this room was built somewhere in the 1950s. It had a little bit of fame because this is where the Disney films High School Musical, this is where they were filmed, in this school, both in the Commons area and in this auditorium. You can see that being old, it has a speaker box up here because architects back at that time, they did not like to have any speakers showing. And so this whole area right in here was covered with grill cloth. It still is, actually, but the speakers have been moved outside at this point. And the original system used Altec multi-cell horns, which, there's been a lot of argument back and forth. They worked okay, actually. Each system that's been in here there's none that's been a real disaster, but they were fine. And I got my first shot at this in the early 1980s, and by then constant directivity horns had been out, and so we put our first system in, but it was almost identical to the multi-cell system in that it was 3 speakers, a long throw, mid throw, and a short throw. We have in Utah, we have almost all of our high school auditoriums fit this pattern. If I take my tape measure here, and if I go up here, supposing we're going to put a center cluster in, and I measure that point down to the front point, that was 25 feet. I let go of it too quick there. And if I measure from the center to the back corner here. That's 97 feet, 98 feet. That's a 4-to-1 ratio. In inverse square law, 4-to-1 means that you've got to make up 12 dB. You have to have 12 dB more going to the back than you would the front. And so this became the dilemma. I started looking at rooms in terms of these ratios when I'm trying to design systems more than anything else, because they were so important. A 4-to-1 ratio is hard to do. We have some schools in the state that are a 5-to-1, and there's even one that's a 6-to-1. They have to be handled totally different. I have not tested whether this LVH system will do them or not, but that's the basic problem that we have. And believe it or not, I mean, I've designed ballrooms, I've designed stadiums, gymnasiums, and in some ways, this room here is a lot harder because you're trying to deal with that ratio. The long throw horns, the 3 horns up in the front that were the part of the first and second system, they have a somewhat problem in the fact that you cannot really array them and get them to come out coherently all the way. And I got a graphic here that is shows this is just a simple ripple tank, and right up here in the corner I've got the 3 sources. Like this would be long throw, mid throw, and short throw. Hope you can see that. This isn't focused in any way, and these are omnidirectional sources, so if they're going to the back at that point, they're not directional sources. But even if they are directional sources, you get this lobing and these nulls, and that's a real problem when you're doing systems. There are people who will argue, no, it's not a problem because people don't walk the floor when they're listening, and they settle in a spot and just adapt to it. But in reality, they're walking in and out of coverage, and intelligibility does suffer unless you're really online with one of the lobes. So that's just a convenient way to show that. So the next system that came along about 2003, next time this came around, was by then line arrays were out. Both modular line arrays and steerable line arrays were introduced in the mid-90s. And in terms of the putting them in this room, I mean, ideally it may have been good to put them up in as a center cluster, but when we hung that, it just got rejected flat out. People just did not want to see that there. And so we ended up doing 2 arrays over on the side, which is very common for stage work. And it's not too big of a deterrent to intelligibility, so that's the way we did them. Now, the arrays themselves were 10 feet long, and so when they would hang down along right here, they would hang down to the point where a tall guy sitting on the stage could reach up and slap the bottom of it. That in and of itself wasn't the problem, the fact that he could touch it. But when we turned this thing on and we're measuring it, you know, we were walking the floor, and amazing how well that it did. You know, everybody was so happy, giving high fives and the whole thing. And but when later in the day, when we went up on the stage with the microphone, you almost couldn't talk because the slap back off the back wall caused from this array being vertical and the beam being too lateral ended up all the way back onto the stage. It was embarrassing, but the way we got around it was we took if you know much about modular line arrays, you put cabinets facing all the same direction to make up for the distance. And so we ended up defocusing that array, splaying the cabinets out a little bit, and then we aimed it down a little bit, and it got to be acceptable. And they used that for another 20 some years, and that was acceptable. The third system we put in was we put a center speaker up here and faced it about here. The 6 dB down point of that horn was here, which was equated to the closer distance, and 6 dB down point was out here. One speaker, however, is not going to do the whole thing, and it's not going to give the sound pressure at the back that you really need. So we ended up putting up a delay ring up here, and that's a method that we've used for years and probably will be for a long time. And this system only went in 2023, and it is very good. But all this while, for the last 35 years, I've been on this crusade with manufacturers. I love the fact that you build a better loudspeaker, but you're not solving my problem. And they would come out, say, with a 90 by 40 or a 60 by 40, and they would give you these two different options and say, here you go, you solved the problem, and I'm saying, well, you guys have a lot more brain power behind you. You need to help me solve this problem. Bring me out a speaker that'll do it. And last year, when we were looking at things with Denny and Chris Barrow came out and Dave Howden came out, and Chris said, we got a speaker that'll do that. And I said, oh yeah, prove it. And they sent me one, and part of our company is a rental house, and we have a huge warehouse where we can hang things. They can't go extremely high, but I can simulate that by getting a 4-to-1 ratio in the warehouse. And there's even one area where I can get a 5-to-1, and I'm still working on that test. But on the 4-to-1, I got extremely good results. These are actual measured results. And when you look up here, those curves are really tight, and the purple curve is 10 feet, the red one's 25, the green one is 40, and the orange one is 55 feet, and they hang in there really good. And I was very, very impressed with this. Plus, the nice thing about it, this over a line array, is that it does have horizontal direct control over it because it's a horn. And some of the times, some of the systems we put in the line arrays, you just get an awful slap off the near wall, and that combines with the direct sound, produces a lot of comb filtering. You really have to pay attention to what you're doing. But this working with this thing is going to be a lot easier. Where we stand right now is we're trying to find a good candidate auditorium to get this into. Like I say, all of them in Utah are about like the one I showed you, and so it's not too big of an issue to find one, but it's more of a political thing. We've got to find a time when it's not being used, and we'd like to have it up for a couple of days, and that's been a little bit difficult, but that's the next step. And then the next week, I'm going to go over and measure this, excuse me, in a 5-to-1 scenario and see how that does. But so far, I'm very pleased with it. Plus, it has the nice feature that it really does sound good. I was an unbeliever, when they told me they wanted to bring a stadium speaker in. I just didn't think they had enough finesse to do it, but it really does sound good. And in tests at the shop, going underneath the speaker, I got very, very good gain before feedback. So I think it has a lot of promise, and it's a little bit new right at the moment, so I don't have an awful lot of data to show you, but as time goes on, we'll get a bunch more. And that's really all I was going to say. So turn this back over to whoever.
I'm going to interject if I may.
Okay.
Thank you, Deward. This has been a fascinating journey, and when Deward shared with me the needs that he had in these, as you heard it, I'm not going to repeat it, you heard it right here from him. And then I was there when Chris Barrow basically laid it out in front of us in terms of what this product could do and achieve. And we set up these tests in the warehouse. We've moved it from one location to another, and so far so good. So we are moving towards a full evaluation in a high school in Salt Lake City. Anyone listening here that would like to participate, I know it's a bit of a trek for some, but certainly are welcome to come and join us. We do not have a date. We are settling into which school. There's two that we're choosing from, and I think they're going to, it'll decide based on schedule and such. But somewhere here very soon, we're going to be doing this evaluation, and would love for anybody that would like to look over our shoulders and listen and see it in action. Just find a way to contact me, and we'll make it happen. Who are we segueing to now?
Can I ask a question?
Yes, of course.
Deward, in your model there were two apparent floors of the thing. One was the height of the stage, and one was where I would presume the floor would be. What was that?
Well, that was the listening plane. In all these models, you don't model the floor, you model up at ear height, and that's
Right.
what that was.
Okay, thanks.
It's kind of tricky when you go to move a SketchUp model into any other manufacturer's modeling program. Some of them will put the floor in automatically, some won't. But we figure it's better to have it there, and then because it's easier to delete than it is to draw. So we put them in all of the models that we draw.
And that's where you put the virtual listening microphones?
Yeah. SketchUp doesn't show any of that. You have to use the manufacturer's modeling to show them, but that's the height that they go.
Thanks.
Any other questions for Deward? We can certainly come back with Deward in the Q&A afterwards, but one more question, anybody? All right, with that, I'm going to introduce Charlie Hughes.
Okay, thank you. Give me a second to get set up here. I thought there
Are
was
we
gonna be some
skipping
other
ahead,
stuff.
Denny? I'm sorry.
Yeah, John, didn't you have some stuff first?
Yeah.
Yeah, that's what I thought.
Sorry, guys. Yeah, no problem. 3, go. Is everything working in the room now? Because I can't see the room.
Looking good.
Power in, John.
Okay, good. All right. So I'm going to cover a little section here discussing how we design and deploy with an LVH system. What's the design process? Maybe we can better address with some visuals some of the questions that just came up. And then Charlie's going to go over some case studies. I'll go over some case studies to show what's happened in our deployments in some actual sites recently. And these are helping us with fine-tuning things in development. So the design process always begins with understanding the geometry of the space, the architectural acoustics, and the locations of seating planes, which is what you were just asking about. So in this model here, this is for me is 5. This light gray is approximately the listening height for a seated listener. And it sits above a marked off area that represents where the seating is. So we need that information, whether we do that in an ease focus model, which lets us look at the model in a couple views, or whether we do it in a 3D model. We need to gather that information so we can build one of these models and work on predicting the sound coverage, and then that drives the steps to get the information into DSP amplifiers to power loudspeakers. Inside of this program called Ease Focus, we have a plugin that's called Venue Polar. And the name comes from the notion that we need to look at the venue and determine what is the polar pattern that fits it. And that's what decides is going to be our vertical coverage. So when we talk about steering, or even when we talked about nominal patterns, we're trying to match the output and the vertical coverage of the speaker to the room. So we start with the room. And the way the plugin works is the designer puts in what are their priorities for the system. There's some choices here about how loud it is, or the maximum number of cabinets you want to use, which audience areas you want to target for coverage. And then it develops an array and suggests an array for you. The array comes as a list, and if you like what it's picked, then you can insert that into the Ease Focus model, and it transfers all the controls necessary to simulate that type of speaker. The Venue Polar plugin also has a loads calculator built in. This is important when you start hanging large, heavy objects from structures. You need to know, A, how heavy are they, so that mechanical engineers responsible for the building can determine the safest way to mount them and make sure it's actually able to hold the weight. But also this lets us see whether the connections between the cabinets are sufficiently safe. So there's three parts to Venue Polar, and this one's actually overlooked a lot, but important for safety, right? Then inside of Focus, there's also a tool called AFMG FIR Maker, or Fear Maker, or Fur Maker. We see it pronounced a few different ways. But what that means is it's making FIR filters, which are I guess you call it a very complex filter, if you will, that manages level and phase angle across a range of frequencies. And applying that filter to each transducer is part of the process of getting the patterns that we develop. So in this application, again, the user puts in their priorities, and FIR Maker builds a pattern to those goals. So at the top, we tell it which areas we want to focus on. Like Charlie mentioned in the video, you can tell it where you want sound to not go, and it'll try to avoid, like a stage, for example. And then you indicate in the software, is your preference to have really, really good uniformity and you're willing to give up some power and output to get there? Or do you want as much power as possible and you're willing to give up a little on uniformity, or something in between? So you have these controls to adjust what is the result. So it's not just automatically always the same goal. You set the goal based on what you want for your project. And then at the end of the process, there's a program that we use called Harmonia Plus, which is provided by an amplifier company named PowerSoft. Many of you probably know them. And we use a set of amplifiers that they make proprietary to us, or OEM to us, I should say, not proprietary. And these OEM amps then can be quickly configured in Harmonia by using a speaker object and connecting it to particular amplifiers, and that programs the amp for you. So you don't have to be good at programming amps. This just sort of puts all the information in there for you. And on a custom pattern or a steerable pattern, what we're delivering is a speaker object to use in the program for that scenario. So those are kind of like the major basic steps to it. I'll show it in context here. For a nominal pattern, the way it currently works in the GLL that's publicly available, all the Venue Polar controls are on the right, and you put your speaker in the location you want to run it. Run the Venue Polar plugin to see what it recommends for an array and how to aim it, and then you can transfer that into the program. And then on the left side, select vertical patterns and run mappings to see what you get for coverage. To execute on this, you would go into the DSP system in Harmonia Plus and just select the pattern that you chose out of the list on the left side, and that programs the amplifier. So that's kind of a 20,000-foot view of how the process works. Stepping through it all is like an hour to do a detailed training, but that gives you the major points of the steps to it. Now with steerable patterns to create asymmetrical patterns, we would still start with venue polar on the right side and develop an array that has the appropriate number of cabinets and aiming, same steps. On the left side, the user now tells the software, do I want to put in the 6 channels of amplification or maybe upgrade to 9 channels of amplification and see what I get for results? And so you select the number of DSP amplifier channels you want to invest in that device. And then, then you open FIR Maker and step through these priorities, top to bottom, making these adjustments to these controls so that it knows what to build for a pattern. Okay, if you've worked in modeling programs, this probably looks familiar. If it's kind of new to you or even foreign to you, maybe it'll make a little more sense if we look at a case study or two. So I'm going to do a small house of worship and a large-ish sort of performing arts hall. I showed you earlier a model or some modeling from this particular site. This room, as you can see, is largely a drywall finished space. So it vibrates, or if you will, resonates a lot in the lower mid-range, and that was a problem. And they didn't want to change the structure or the surfaces to modify that. And the seating has a certain geometry to get coverage for. And their previous system had really good speakers, but it wasn't sufficient for music and singing and clearly hearing the audio system along with the singing. It was kind of okay for public speaking, but not for the worship music. So in this case, I put in 2 LVH systems, one on each side to address each side of the room, right? There's another view of it from down at the first level, right? And we used the 60-degree nominal vertical pattern, which I showed you earlier and looks like this from a side view. So if we were to capture the sound in the air, if you will, and look at a section of that projection, that's the vertical pattern. I'm running in this model what's called relative SPL. It's showing you how much the sound is changing, not what is the amount of sound level. And so everything inside the green is within 3 dB of each other. And anything in the orange or red is 2 dB. So total of 5 dB variation, or 2.5 across the front to back in this room. Top view, along with some frequency responses, shows us what you saw earlier for the coverage using a nominal pattern. And then you'll see this black line. This is something Todd mentioned earlier. The black line refers to flag number 7, if you can see that sitting on the platform, approximately where you might have a microphone. And you see it, the level of sound for mid and high frequency is much lower on the platform than in the seating. So that gives us a lot of capacity for gain before feedback, number of microphones in use on stage. This is the SPL. Their target was 90 plus or minus a few dB. And that's about the level that they like to operate their music. Now, something that was mentioned at the very beginning that Denny pointed out is his LVH can get loud. It can get 10 dB louder than this without even trying and sustain that for a very long period of time. But in this case, obviously, we're not using all the power of the LVH. We're using its pattern control. The next case study is fairly different, a little closer to what Deward was talking about. So this is 2 views of the room. The left side, you're looking onto the stage from about mid-house, and you should be able to see between the reflecting panels some black speaker objects that are kind of hiding in the shadows. This is exactly the aesthetic that they wanted to achieve. They didn't want the audio system drawing attention to itself. We had even talked about having long line arrays that hung to the far left and right of the stage along this side wall or something like that. They just didn't want to look at all that equipment. And they had already designed all the acoustics for the space, which were well done. It's a very well-behaved room for its size, so that was very nice, but they just didn't want to have big equipment hanging down. They just didn't want that look. They do a lot of fine arts in this room, and so that doesn't really go with the fine arts aesthetic. So that made sense. The picture on the right is from the stage looking back, so you can see there is a balcony and then that system of reflecting boards above and some absorption panels and diffusers on the side walls. So the original design for this was to use basically 4 zones of speakers. So he had 3 LVH, and this is easier to see in the section view at the bottom of that image. We had 3 LVHs stretch across the stage, each one covering a good portion of the first floor. The room's 120 feet deep from stage curtain to back wall. So it's a really long distance to get to the back, and our trim height is limited to 23 feet. So this is in the neighborhood of that 5-to-1 or a little more than 5-to-1 ratio like Deward was talking about. So in this case, the balcony had its own set of speakers because it's a big enough area to need it, and it's far enough away that it needed it. Under the balcony was also outside the reach of the main speakers, so it had, this design had 5 under balcony fills. And the front row, it's sometimes nice, even if you don't have a coverage problem, just to have the localization benefit of having speakers right in front of you if you're in the front rows. It sounds like you're listening to a performer on stage rather than listening to a sound system that's hanging over your head. And this was a great design until there was a major snafu with the budget for the project, and we had to remove everything except the 3 main speakers and a pair of subwoofers. And this was really bad news because now we don't have any sound for the balcony. We have very little under the balcony, and the front isn't getting great coverage either. And this would have been a major problem if we didn't have a new option that had landed a month before I learned of this. And so I took the new design files we had for LVH and made an attempt at, can we recover some portion of this project with just the LVHs we have and see how much we can promise on improving things and reduce some of the ill effects of not having all the other speakers. And so this is the steerable pattern in its section view of just 3 LVH cabinets and 2 subwoofers all by themselves. And you'll see in some measurements I took that this is approximately what we got. In fact, the balcony came out well enough that the integrator wasn't sure he was going to be able to convince anyone that they need speakers up there someday. So in this view here, the pink line is the balcony. It's the lowest response line, averaging the responses in the balcony. And everything else is the first floor seating, the green, orange, and the 2 blue zones, just different segments of the seating front to back.
Hey, John, do me a favor, roll back and do a before and after again. I'd like to see that.
Sure. So this is what we would have had if we didn't have a way to alter the vertical pattern, right? And then here's the result after applying the steerable controls for LVH. One more time?
Oh,
It's
sure.
like going to the eye doctor. You like A or do you like B? I'm going to go with B. Yeah. We got one more of the set of measurements here. This was using what's called a moving mic average, where we move the mic and collect a very averaged response of the space. And this is the first floor measurement. So getting surprisingly good results. The high frequency does roll off when you get underneath the balcony. So if you're all the way on the right side of that drawing near flag 1, which is where the mix desk is, you're not getting all the highs, but you're getting pretty well everything else you need to be able to operate the mix board accurately. So not a total success. They did leave in a contingency because actually the conduit's installed should they decide to do the over balcony system. But strangely enough, the results came off good enough that they felt comfortable opening for what's basically the performing arts hall for the region, and to be able to host shows and different kinds of events there, not just for the school's purposes, but as the regional community theater. Last thing we measured around the room was the speech transmission index. We used a stipometer. NTI makes this XL2 meter. They've recently released the XL3 meter. And this is a method to pretty quickly ascertain whether or not a seating position is receiving intelligible sound. And so these are various positions around the room, measuring the STI before we did some system equalization and after equalization. Some went up, some went down, and the average was actually equal. All right, ready to pass off here to Charlie.
Okay, thanks, John.
I'm going to stop sharing here for you.
Yeah, give me a second here. Let me share my screen.
Yep.
Charlie, sorry I jumped the gun on you and almost omitted that beautiful stuff from John. As you're getting ready, I'm going to mention, had an opportunity to do a demonstration in Grants Pass, Southern Oregon, for an install in the River Valley Church, which has 6 of these cabinets. There's actually someone in the audience here who is an audio professional, front of house engineer, consultant, and a rigger. And you hung 6 of those cabinets. We are actually going to be doing a showcase in 2 weeks, which we'll talk about at the end of this. But one of the things that we did in that demonstration, when we brought in a cabinet in advance, didn't have a place to show it except for the 1950s wood structure that was the Josephine County horse arena. It's a rodeo arena. And in the process of showing the church the 55 feet back into the dirt area where the horses usually run, we were playing that for them with that preset because that's where the back wall, they had to imagine a back wall as they were listening, because that was the demo and that was the space that we had to do it in. But then we decided, well, wait a minute, we've got 200 feet of space in this venue. So we switched into another setting that was addressing all of the wooden seats that surrounded the area. And that's when I realized that we had a system, as you saw in that, was that Cuyahoga? Is that how that's pronounced, the high school there, John? I think it is. And they, you saw those 2 settings, the ability to do 2 different presets, not something you could switch fast. These files are big. It's something that you would set up for a venue. And so now we have an application. I'm working on a project now with a consultant where we are doing 2 different settings for this. Again, the same speakers, it's hanging exactly where they are. They're not moving, but 2 different settings, an adaptive coverage, if you will, where the balcony's in use in one case and the balcony's not in use the other case. And there's 2 different settings that accommodate that. And with that, Charlie, I think I've burned enough time. You're hot and ready to go.
No worries. Yeah, so I'm going to go over a little mini case study of a recent installation of LVH at a church down in Grants Pass, Oregon. We'll look at some simulation data that was generated during the design process for that installation, as well as comparing that to some of the measured performance of the system, measurements that we gathered during the initial commissioning. So what you're seeing here is the plan view of the sanctuary with the loudspeakers. This was done in Focus 3, East Focus 3. So you can see the seating areas shown here. These are loudspeaker locations. These are all muted for the data that I'm going to show. We're going to concentrate on this loudspeaker over on the house right side. This loudspeaker was one of the ones that was part of the stereo array for the system, attempting to cover a majority of the seating area. And you can see these little flags here. These numbered flags are microphone locations. We'll use those to investigate the frequency response, both of the simulations and the measured response at very similar microphone locations. Before we get into that, though, I want to highlight something, and John alluded to this earlier. it can be very helpful to see what's going on, visualize this by looking at the radiation pattern of the loudspeaker. This is a side view, and you can see the radiation of the loudspeaker, the radiation pattern of the loudspeaker. This is at 2 kilohertz. This does not have any custom beamforming optimization on. This is a standard pattern, very much what you would see out of any constant directivity loudspeaker. In the audience area, the listening plane, the coverage is fairly uniform. Nothing to that you'd sneeze at, but it can be better. When we turn our FearMaker optimization on, we get what we'll call an asymmetrical directivity pattern in the vertical plane, and that gives us a constant coverage in our audience area as opposed to constant directivity. You can see that the energy is much more focused on the seating area, and there's less extraneous energy being directed to other places. You can compare the two side by side, constant directivity with no custom beamforming on the left, and the custom beamforming constant coverage on the right, and see that there's a lot more evenness of coverage front to back in the seating area. Also, the lobe, energetic lobe of sound going up here, the level is much reduced when we get over here in the constant beamforming. There's going to be a lot less energy into the reverberant field. You're not going to have nearly the level of reflections off the ceiling that you would have in the constant directivity case. So looking at the frequency response at some of those microphone locations, we can see those here. The frequency response is pretty good, pretty consistent at the locations, but they're at different SPLs. So you don't have the same loudness front to back in the venue. When we turn on the custom beamforming to get that constant coverage, you can see that the grouping, the consistency of SPL is much more uniform front to back because the grouping of those frequency response curves is much closer together. Looking up at the top graph, we've got a variation up from 7 to 12 dB in all those curves, whereas the bottom group, you're in the 2 to 5 dB range. So it's going to be much more consistent. Sound quality is going to be much more even across your entire seating area. One other thing I'll mention is that grouping of curves on the bottom. It's going to be much easier to equalize that and get a consistent response throughout the venue. One thing I should mention here, I've pulled out the data out of eFocus and then applied our array EQ, our voicing EQ to the loudspeaker. So instead of having this very jagged up and down frequency response, now we have a much more even flatter frequency response that yields that target response, the target sound quality that we want out of LVH. You might notice there's not much going on below about 90 or 100 hertz. That's because we're just looking at LVH here, and there's a pretty big, powerful subwoofer system in this installation, and we're not looking at that. So you're seeing the high pass effects of the crossover filters that we have there. But good even response front to back. Now, if we look at the direct sound only out of the loudspeaker system, no reflections or anything, this is the response that you'd see if you measured the loudspeaker in anechoic chamber or free field conditions. This is the exact same loudspeaker data that was used in the simulation in Focus, exact same GLL, but I pulled much higher resolution data out of Speaker Lab, another modeling program we use, so you could see what the direct sound would be. Like I said, high resolution, you can see some more details in what's going on in the sound in those frequency responses. And here we see the actual measured frequency responses at those same mic locations. Here we have room reflections, nearby boundaries that's giving us some different loading conditions, room modes. All those cause response variations that can be very difficult to eliminate from the measurement data. I think about a 50 millisecond window was used on this data. So we could still have some good low frequency resolution and see what's going on down low. The trade-off for that is you're going to see some dips and bumps due to room acoustics, and we have very little control over that for the direct sound coming out of the loudspeaker. Notice though that the response variations are still quite good. The grouping is fairly well together there. There's another way I've come to look at frequency response consistency, and that's to calculate what I call the frequency response range. To do that, we'll use all the response data for one of the data sets, and we'll calculate the average response and the response envelopes, upper and lower response envelopes from that data. You can see here that you've got that average response in red, and then the envelopes, upper and lower envelopes in black. The next step is to use those curves, and by subtracting the average curve from each of the envelopes, we get what I'll call that response range, these pairs of curves. So for the Focus 3 simulation data, we have these response range curves, and you can see that everything is within about plus or minus 2 dB from 400 hertz up to 10K. So very uniform response front to back in the venue. If we overlay the response range for the direct sound, we see that there's very good agreement with a few small exceptions in the higher frequency region, but the trends are right there with each other. The measured response data shows very similar trends, slightly larger range deviations in some regions, but the overall trends are right there. I should also mention that some of the differences that you may see here in the measured frequency response are because this is a completely different loudspeaker from the one that was used for the modeling data set. So you're going to have manufacturing tolerances and other things that are going to drive the response to be a little bit different. All things considered, though, we've still got very good correlation between the measured data and the simulation data. One of the last things I want to show y'all is a comparison of the frequency responses at the actual mic locations. So in this last set of graphs, you've got the Focus 3 model simulation data shown as the red curves. The direct sound only is the blue curve, and then the measured response in the room is shown in green. These first two mic positions are very close to the loudspeaker in the front of the seating area. You can see even up front, we've got very good correlation there between the simulation data and the measured data. We move a little bit further back in the room to these two mic locations, and I'd say here you've got great correlation. There's not much difference at all, particularly at the mic location shown on the left. At the right, in that 2 to 3 kilohertz region, there's a little deviation in the measured response, but overall still really good. Then we move way back in the room, so we're at the very back here. You're going to get a lot more of the room modes and cone filtering due to reflections getting into the measurement data. And you can see that particularly at the graphs on the left. But if you sort of visually average out that green curve and the cone filtering you have there, you can see it does exactly what the simulations show. Then at the one on the right, above about 300 or 400 hertz, still very good agreement with the simulation. You've just got some room stuff going on below about 200 hertz. So the end user customer, front of house mix engineer at this location, the reports we got back, they were thrilled with the sound quality in the room. Very tight uniform response all over the way it integrated with the subwoofer system. They were very, very pleased with. With that, I'll turn it back over to Todd so we can recap things.
Awesome. Thanks, Charlie. And thanks to John, Deward, and Chris Awesome information. Lots of information, obviously. I'm sure there's probably curiosities out there for how we did all this, more of this data, looking at the measurement data. To me, when we can marry prediction data to measurement data, that's like job well done. We try to be very honest in our spec. It's difficult to do in spec wars out there. But when you see results like that, I mean, you got to high five the guys who put those speakers together, and never mind commission them, and to Charlie for the voicing filters. So anyway, I get pretty passionate about this stuff. Our VP, my boss, calls me too passionate, but I like passion. That's part of what we do here. Nonetheless, any questions kind of hanging out there? We can leave this open if there are any questions in the chat. Jess, maybe you could toss those at us. So at least let's open it up for any of that kind of proceedings.
I've got a couple questions about the physical box. What's the definition of cover slot?
So yeah, there's some plastic plates, polymer plates that cover the entrances of the low frequency woofer energy into the horn. We don't just have holes cut into the sidewalls of the horn. We've got cover plates with some engineered slots of different orientation and different widths in there to help make sure the energy enters the horn more properly in a more optimized manner. I don't know, maybe we can, I don't know if you can pan the camera over. Well, the LVH we have in the room is face down, so you won't be able to see the cover plates. Yeah. I don't know if
I'm putting up an
John,
image
you or
that might help
Chris
you,
have
Charlie.
a slide showing the front of the horn without the grill on it, where you can see those cover plates. That might help answer. Dan, yeah, there you go.
There you go. Mm-hmm. So there is a hole or 4 holes cut in the walls of the horn, and the plate goes between the driver and that trapezoidal hole?
Yes.
Okay. Okay. And in that picture on the left, you can see the distance from the front of the horn, the front of the cabinet, to the back of the high frequency drivers. And when you showed another picture showing the full cabinet and this from the side, it looked like that distance from the back of the drivers to the front of the horn was half, roughly, the depth of the overall cabinet. Is that space for the woofers to...
He's talking about the rear chamber, I think, Charlie. Maybe back
yes.
up a few.
Yeah, that rear cover. Go back to this, there you go. So right. you can see there where the back wall of the enclosure is relative to the high frequency drivers.
Yes. And we're looking down on it now.
Correct.
And we're looking at the bottom of the cabinet, the gray area.
Yeah, you're looking down from overhead. Yeah.
Yeah. So we're looking through the entire cabinet to the bottom.
That's right.
So this is not a ported cabinet at all.
No, it's the low frequency section is a sealed box.
Great, thank you. Okay, cool.
I have a sort of related question. The slots for to keep the mid-range from reflecting.
Yeah.
You say that there's a magic material in there that is an acoustic absorber. And I'm thinking of other magic materials, to wet urethane foam, that has turned out not to have good longevity. And hopefully the material science has been done that's not going to break down. I've got some rather nice microphones where they used urethane foam as a suspension for the capsule, which of course is broken down and it's completely unobtainable to get anything that's a correct replacement.
Sure. No, it's not. I can tell you, it's not urethane. It is. It is a foam, but it's a different kind. Yeah. And
Yeah,
luckily we're not. It's not exposed to too much UV being inside. I mean, it's really
sure.
encapsulated and inside the cabinet. I think UV is usually what does most of the damage to those things.
Okay, good.
We have a question in the room here.
We're not hearing the question.
Yep, hold on.
I'm curious, is there a phasing plug that goes in?
Is there a phasing plug in the M200?
Yes.
Holding the M200 diaphragm.
Excuse me.
I assume people know what that implies, but
Yeah, the
piece he's holding, I
M200
think,
is
is
a
the
very low.
diaphragm and the phase plug, right?
Yeah, that's the diaphragm.
Okay.
The diaphragm is glued to the phase plug. It's a very low compression driver. There's only a 2-to-1 compression ratio on that driver, which is one of the reasons why it has vanishingly low distortion. We love it so much for that. And also it's why it maintains its sensitivity in lots of loading conditions, and a lot of compression drivers don't do. Yeah, so it's basically compressing around what looks like the surround to you, and actually the dome in the middle doesn't get any compression at all.
I'm holding this up towards the camera. I'm assuming that that's the side that faces the horn.
No, the side with the voice coil faces the magnet. Yeah,
Faces the magnet. Okay. Well, I mean,
yeah.
but still.
Oh, so yeah, if you can show you how it goes on there.
That's corrective.
Okay, that's the way. Okay, so
Yes, like that.
okay, thank you. That explains it to me.
To show the camera, is this?
Yeah.
That's the exit.
Okay.
That is now
Okay.
placed onto the.
So it's just an open. Okay. All right.
And that's
the metal gasket plate that's on the opposite side, is that just a flat metal plate, or does that have some interior shaping to it as well? So looking at the example on the stage, opposite the horn throat entry point on the driver, there's a blank metal plate on the other side of the mold. Is that just
Yeah, I
a
mean,
flat
there's
plate?
there's some special shaping that goes on. I mean, there's 2 different pieces of metal there, and of course, to make the gap as high energy as possible, there's some special
Yeah.
shaping going on both the T yoke and the flat top plate. But it's just it's
Okay.
essentially
So
a
there's
flat plate behind there. But
Some curvature to match
yeah, there's some angles going on in the metal to concentrate the magnetic energy. Yeah.
cool.
I'm thinking in terms of the old Altec and JBL drivers where the phasing plug is part of the magnet structure, if you will.
Yeah, this one operates a little bit differently. The magnet is really on the back side of the driver, and you don't have the sound energy going through any part of the magnet structure on the M200 like they do on a lot of conventional compression drivers.
Thank you.
Any other questions?
Great. We do not have any questions in the chat, so we're clear there.
I'm curious about the high frequency drivers now. I'm curious about the high frequency drivers in that system, but
I mean, those are not drivers we build in-house. Those are drivers that are purchased. But I mean, like everything in this cabinet, we try to everything that was possible to fit and pick the ones that we met all of our goals for power handling and SPL and of course sound quality. So in a lot of our speakers, we're lucky that we're able to match the M200 diaphragm material. It's actually the same diaphragm material that's in the HF driver, so they sound a lot alike. LVH has that. Our I-Series point source cabinets have that as well. We try to do that wherever we can.
But and Chris, the mid-range driver, the M200, that is manufactured by in Chester.
Yeah, that's manufactured in Chester, PA. Yep, in our factory.
Okay, so that's our own manufactured, and that is a derivative of a driver that I'd mentioned earlier called the M4, and that was a 4-inch driver that was quite extraordinary, never been done before, never duplicated since, but this is a derivative of that technology.
Yeah, and this M200 we've been using, since the 80s at least, and we've been in a number of different product lines. It's really been our key product for years. If anybody, if people do know, community loudspeakers is usually for our R series, and in our, R2, our largest member of the outdoor line, that M200 has been in that speaker for the last 27 years and going strong. So it's part of our voicing and sort of definitely part of our heritage at this point. But a lot of our speakers use that driver and have similar tonality from one to the other.
Is there anything else we need to do? One more question here.
Noting the, you mentioned earlier that 8 kilohertz notch. I'm sort of wondering, you have that backwards forming wavefront that is headed towards the high frequency drivers. Are they reactive enough that that could be absorbed electronically with them? Do you know what I'm?
I know you're asking, but I don't know that we've looked at that. I mean, we came up with we wanted to solve things mechanically first, and only apply processing when necessary, because philosophically, that's how you're going to end up having the best sounding speaker if you get it physically right first. So that was our goal. It was 800 hertz, not 8 kilohertz. 800 hertz.
800 hertz. I'm sorry. Yes. Yeah. Okay. 800. I mean, if the drivers, the high frequency drivers, can't react to that low frequency, then forget it. But.
Yeah, and there was a graph showing a tiny bit of attenuation below 3 kilohertz or something in the HF driver, but again, not enough to affect where our crossover point was or where power handling was, so it just didn't matter. We had to you got to trade off something to get something. There's it depends, right?
Yeah, I actually had another question. When you start using the beamforming capabilities, how much headroom do you give up?
Oh, that's a great question. A lot of times it depends on how aggressive, how aggressive we're trying to do the beam forming. Sometimes we're not giving up very much headroom at all. Other times, if we're going for really high uniformity and trying to do so in a audience coverage area that's very difficult to do that, you may be giving up some headroom. Fortunately, in the FearMaker optimization GUI, as I think John alluded to this, there's a set of controls you can adjust to.
I'll put it up.
Go one way or another. Do you want to get high uniformity, or do you want to maintain high power output and limit the amount of headroom that you're giving up? You can also adjust those. You're showing a great slide of it here. You can't see it here, but there's some advanced settings that you can go into and actually customize those and sort of build your own trade-offs, if you will, between a high power and high uniformity. So it's a trade-off, and it can be done on a case-by-case basis.
Okay, so it's not something that's going to be dynamically available like some other speakers I can think of.
No, it's not something that will be adjustable or trade-off at runtime. You've got to make those selections and trade-offs at design time.
Okay, thank you.
In this graphic here, what does ignore mean under audience areas?
So go ahead, Charlie.
Go ahead, John.
Well, I would say in one of the examples I showed, I was using avoid. Probably your question is, what's the difference between avoid and ignore?
Yes.
Okay, so the avoid is telling the software for this area, in this case, the stage, try to not put sound on the stage.
Yes.
Ignore means don't do anything. Don't put sound there. Don't not put sound there. Just
Leave it as it is.
Leave it as it is.
However it
whatever
comes up, you leave it alone.
Right.
Got it.
So let's say I had the front and rear center areas here in the stage set up like this. Maybe I had another area that was maybe behind the back row, some mezzanine back there. I might tell it, ignore that. I want to plot it so I see how much sound maybe is getting past the back row into that area or something, but I don't care to optimize for it, right?
Got it.
So, yeah. And part of the design process is iteratively to tinker around with some of these things and try different things. And sometimes place audience areas in a place where you want to kind of create a wall, if at least, or sort of virtually a wall to tell the software, don't put sound here, because maybe there's a surface we want to really be careful to avoid because we know it's going to be a significant acoustic reflection problem or something like this. So
Yes.
and I think the fader thing you were looking for, Charlie, was this one, right? If we select custom, this expands the GUI a little bit, and you get 4 faders to adjust different parts of the loudspeaker performance to kind of fine tune this. Yeah,
It's not worth it. Use the buttons.
I just use the buttons.
Yeah, one of the things I'll do, like John was talking about, if you see you've got you know, a lobe headed somewhere out of your array after you've done an optimization, and you know it's going to be a problem, like the slide I showed where there was a lobe headed towards the ceiling. I'll put an audience area on the ceiling. You're never going to have an audience there, but once I put that audience area there, I can tell FearMaker to avoid that audience area and try to not put sound on the ceiling, which is generally a good thing to do. And you may end up with a better overall coverage pattern.
I think in your case, that smoothed out that polar, right? Because it probably had lobes after doing, the first passes on that design, if I remember right. Yeah. So you can think of audience areas as targets and boundaries, right? What to shoot for, what to not shoot for, and you can put them anywhere, not just what you're going for, which is an audience. Yeah.
With
Just a
this,
creative way to
I'm
use it.
going to show a project I've been working on here that shows that. So this is a large area that's going to be a multi-use, originally designed to be a drive-in. They coined the term auditorium. It was kind of cool. But the issue was this represents the building face. So this is as steep as I can draw an audience zone in ease focus. It's probably kind of hard to see. Looks like it's all right. But while there's still some fine tuning I'm doing to this, but you can see how it split that beam, right? So now I've got energy going across my audience zone that I've defined, but this building is literally smack in face of the aim lines for the speakers. So, and like 300 feet away. So you can imagine the nightmare of a reflection that we're going to get off that building. But by using custom beamforming, I'm minimizing the energy back there to a very appreciable degree. I'm looking at 2.5K, 3 octaves, and getting about 8-9 dB of attenuation in that critical voice band off that building. So makes for obviously a very much more amenable acoustic performance.
A few minutes ago, somebody mentioned, and I'm sorry I didn't register who it was, I couldn't tell, about making loudspeakers sound one like another so that the voicing was similar from one model to another. How important is that to loudspeaker manufacturers, and what factors enter into voicing, if that's not a too hard question?
Charlie, you got that one. I mean, it's definitely very important to us. But yeah, Charlie and I have discussions about this.
Yeah, it's something that we feel is very important and that we strive for, because somebody like John or other consultants, integrators, design build firms that are designing a sound system, they're not going to use the exact same model of a loudspeaker everywhere. You may be using an LVH for your mains. The architecture may be such that it's impossible for that mains loudspeaker to cover under a balcony. So you're going to have to use some under balcony fills. It would really be great if that mains loudspeaker and your under balcony fill loudspeaker can sound as similar as possible. That's going to make it easier on the folks doing the installation and commissioning, less equalization work to do. Hopefully they sound as similar as possible right out of the box with the DSP settings that we provide to optimize them. There's always going to be some on-site adjustment, optimization, EQ that has to be done. But if we can make them sound as similar as possible and minimize the work that our customers have to do, then we're making it easier on them to get to where they want to be.
Can I add a little more to that, Charlie?
Please.
Yeah. So I think there's two ways, two aspects to this. One is applying filters and optimizations to the speakers so that they respond similar, right? Their responses all agree. I think that's one of the aspects. The other one that Chris mentioned earlier, he talked about the high frequency driver and the mid driver in LVH in particular, and in three-way I series. The driver diaphragm is made out of the same material. So all materials that we use for drivers, whether it's the cones or the mid drivers or compression drivers, they all have a natural sound to them that you can't entirely get rid of. It's akin to picking different kinds of wood to build instruments, right? And so if you want to build a family of violins or guitars, you're going to make them all out of similar materials, even if they're different sizes, right? To get some similar properties. So you wouldn't mix necessarily. So it's a similar idea here. And part of the auditioning process for drivers here is, do they pass certain technical merits? And the other one is to listen to it. Do they sound like they belong in the same room together? So that as you move from one zone of a room to another part, like Charlie's talking about, the under balcony or out into the main house, it all sounds like it all came from the same place, made of the same stuff. Does that make sense?
Yeah, definitely.
Yeah.
And what parameters are you looking for there?
So some of that's subjective and some of it's objective.
Right.
Right. And it's usually a process, or at least when we've done it, we begin with, when I say auditioning, literally taking drivers through a testing process to see, do they technically need to provide the range they need to provide, the level they need to provide? Are they uniform? Are they going to take a lot of attention in the equalization to fix problems, right? This sort of thing. And then whatever rises out of that process usually is what gets evaluated subjectively to see, do they have the distortion characteristics, which is really hard to quantify distortion. You can make distortion graphs, but it's hard to hear it and point to the graph and say, that's what I heard. So
yeah,
there is a subjective kind of last phase to that.
I hear this conversation as to the drivers. There's the question of how do they react to the amplifier that they are connected to. And I know there are things like negative impedance amplifiers or zero output impedance amplifiers, or you go matched impedance or transconductance. And you have all of these strange options. And of course, there are variations in distortion through all of this. And part of it can be crossover related. But is that something you're paying attention to, I assume?
Not so much. Most all the amplifiers that we're using these days, modern sound systems, being constant voltage sources, eliminates a lot of those problems. There are some things you can do with variable output impedance amps, nulling out the effects of or improving the damping at the loudspeaker, basically taking the resistance of the wire, the cabling between the amp and the voice coil of the driver out of the equation. But you've got to be very careful in doing so. It's not something that we do as a stock setting for people, because if you get it wrong, the amplifier will go into oscillation.
Well, I have had the experience of building a negative impedance amplifier. People aren't seeing me, but in that the voice coil of the woofer was almost frozen, except at the very low frequencies. You could push it, and it would oscillate at about a couple of hertz like that. If you tried to stop it mid-travel, it blew all the fuses in the amplifier right back to the power supply. Those were 3 amp fuses at 16 ohms, I'm sorry, which was way over the power level that the speaker voice coil would tolerate. And it survived because the coordination was appropriate for the fuses. But I kind of ended the experiment at that point because I couldn't replace the woofer. So.
Yeah, our ALC amplifiers that are OEM'd for us by PowerSoft, the output impedance of those is variable and controllable within the Harmonia Plus interface, the software there. So, somebody who is doing an installation, if they really want to, get aggressive about this, they can meter the impedance of the loudspeaker cable between the amplifier and the loudspeaker itself, know exactly what that is, and dial in, I would say, just shy of enough negative output impedance of the amplifier so it doesn't completely cancel that out, but that's your safety margin to keep it out of the range of oscillation, so that you don't let the manufacturer installed smoke out of the sound emitting devices.
Brian Willoughby had a comment, and Brian, can you unmute and say it rather than me reading
Yeah,
it?
I may have been misinterpreting, but I thought part of the concern was that when you're putting a tweeter and a mid-range in the same speaker, and they're going to be reacting to a crossover where at some frequencies they're both reproducing the same frequency, that you want the materials to be similar so that the sound of the two drivers that are cooperating in that frequent crossover range are compatible. Is that what you were saying, basically?
Yeah, exactly. I mean, it's very difficult to hear a transition in the crossover when using drivers with the similar diaphragm material. We've repeated this in quite a few speakers at this point, using the M200s and drivers with matching HFs.
Thanks.
And of course, it has to do with the crossover as well. I mean, we've done it in passive crossovers where it's a little trickier, and in the LVH, of course, it's electronic crossovers between everything. So,
thanks.
Anything else?
All right. If not, I think we'll probably start wrapping it up, at least for the in-person. Denny, do you want to have some closing remarks?
It's a trek for most, but in 2 weeks, on the evening of Tuesday, March 10th, and all day on Wednesday, March 11th, if anybody would want to come to Grants Pass, the nearest airport is Medford. Please find a way to get in touch with me through Jess, the AES chairman of the Pacific Northwest section, and let me know. Be happy to. We have 6 cabinets in a church, 750 seats, and Dave Howden is coming out from Chester, Pennsylvania, to do a refinement of the tuning, and that is going to be a showcase moment to do extensive listening and evaluation. And with that, Luke.
Thanks, Denny. And with that, I think we'll close the in-person session here, start kind of wrapping it up, tearing it down, and the online Zoom meeting will stay open. Is that correct, Jess?
Yes. Thank you so much, everyone. Tremendous job. This was incredible tonight. Huge kudos. Just thanks to everyone for all your hard work and efforts in putting this together. It was outstanding. So we really appreciate it. And thanks to everyone for being here. And yeah, we will disconnect from the in-person and we'll keep the Zoom room open for a bit so folks can chat and hang and talk about whatever. I may need to go let my dog out, but we'll keep it going.
Who
And
let the
Thank you
dogs out?
so much, folks. Really
Yeah.
appreciate you.
Yeah. Yeah. And to all the presenters online, that was fantastic. The science behind it, the history, the development of it, the particulars, some of the secrets, having that back reflection is very interesting, and the solution for that I think is very cool. To the real world applications, that was plus or minus 2 dB across an entire venue. That's fantastic. Like, that's bonkers good. And the box sounds good too, to top it all off. So yeah, thank you everyone for putting that together. It's no small feat, wrangling everyone, and figuring out content and putting together the presentations, the multiple presentations. So
And you guys
greatly
figured out the
appreciate it.
video screen.
Yeah.
Yeah. Congratulations.
What,
Yusef, thank you.
What happened?
Fearless operator back there.
What was it?
I don't know if he wants to talk about what it was.
The hamster got tired and wouldn't run around as fast as he needed to.
Power bill.
Power cycle everything, I think is what it was, in a particular sequence,
Restart
because it's a
Windows.
network. Yeah.
what's the weight of the box?
250 pounds for the indoor version. It's about 220 for the outdoor version.
Okay. I thought my SLS 960s were heavy.
And it rigs from top and bottom, or just top?
Sorry?
It rigs when you hang it to get a particular angle. Are you grabbing just the top, or the top and the bottom, or?
It depends on the down angle of those. So the bumper for hanging these things can also be used as a pullback.
Okay, so there's a separate bumper involved with this.
There are some multiple hanging options. There's a bumper bar that one would use if you can use it with a single or multiple boxes. I believe there's a yoke to use for single box applications.
Okay. How heavy is the bumper?
It's hung in this.
Can't quite hear you.
Here we are.
Correct. The steel
It
bumper
has
is
to.
probably
It
about
has
40.
to be hung so that the horn you see here is in this position, which could be this way or that way, but not sideways, as I understand it.
Correct. You don't want to.
Yeah.
So if you wanted variable horizontal directivity, you could hang it sideways and do that. I don't think we've run into that application yet.
Right. Okay, so I'm seeing all the hang points in the middle of the white one.
There you go. Yeah.
Yeah. And there's, the sides inside the box, the sides of it actually have steel going top to bottom inside of both sides of the box. So everything grabbing side to side is actually going fully through steel and not actually through the materials you're using for the enclosure. So yeah, you can use eye bolts, you can use the grids, you can use the U brackets, you can use what we provide. Our good friends at Polar Focus make a bunch of other things that interface with the grid that we make.
Cool. How much did the bumper weigh?
I don't know an exact number, but if I had to put a number on it, 40 some odd pounds.
Yeah. Okay,
Yeah.
great. Thank
I
you.
think it's a bit more than 40. I've lifted it a few times. It's more like 60.
Is it? Well, you like to
believe
just
that,
work
too.
out more than me, I guess.
And
we have
these
software
side
to answer
panels
this
are-
question. Maybe we
These
should
side
check it.
panels are what's connecting the two boxes together, these plates.
Yeah,
and
those
there-
side panels, there are multiple holes in them to govern what display angle between the adjacent cabinets is.
Okay. That isn't quite showing in these pictures. Looks like the white one is narrower than the dark one on the right.
There are
Well,
two different plates.
Two different plates.
Yeah.
The
Okay.
white one has three sets of positions. to put the cabinets completely in contact with each other, or actually, if you look at the left side, you can see it. If you flip it around, you can also use it that way. So that's very modular. The one on the right is specifically for that particular setup, which is the dual cabinet 20-degree setup.
Okay. I had another question for you that I completely forgot about. But when you were showing the pictures of the single point source cabinet versus this, you first showed a picture of a line array of, I think, 6 boxes compared to one of these. But then you had 2 heat models showing single box compared to this.
Talking about the very beginning?
Yes, it was very early on.
Let me bring that up.
Very early on.
Go back to here.
And it seemed like the comparison was, nope.
Was it when I was talking in the very beginning?
Maybe. This isn't it. The first picture was
I think, Todd, you have
I think it was my
a
intro.
line array on top and the single box LV, the box we're looking at down
LVH,
below.
yep.
This is almost it, but it's not it.
So this scenario is a comparison of, here's the line source, 5 cabinets tall, in exactly the same position as the LVH. And then here's the LVH with the steerable beamforming applied.
There was
Todd, did you have another one
picture
prior
with
to that?
2 versions of the heat map down below. 2 of those side by side, one above the other.
Is it this one? Are you seeing? No.
No.
What am I sharing? The wrong
We're
screen.
seeing your OneDrive Wavetronics folder.
Yeah. Stand by.
Sorry, I was confused and forgot. But
Given
reminded
the
me.
FIR maker software and software iterations.
There we go. Here we go.
This one, okay.
So that upper one is a single box of some sort?
That's a single point source 12-inch two-way.
Okay.
It just happens to be right behind the LVH.
Go to the picture before this. Yeah, so you're comparing the LVH on the one side with a 6-box line array on the right side.
So we kind of just visually wanted to relay the message of the scale between this. So yes, there's a 9-box array in the wireframe there with an LVH. The one I just put IV6 there. It's literally just a product marketing photo. I didn't have a photo of a 9-box array to match to that.
Okay, but in the next picture, we're not seeing the line array compared to the LVH.
That's
We're
correct.
seeing the point source. Do you have a picture of the line array compared to the LVH?
It's probably in my design file that I just didn't slide over to this.
Okay. Just
But
curious because we were.
For sure. We kind of narrowed it down just to looking at a point source next to a new type of point source, just to prove the point here, right?
Exactly.
And then develop the story behind the LVH versus a line array in the section that John went to with the church. So
is the line array more similar to the LVH in pattern?
Correct. So this was all derived from that initial meeting with Deward and Chris Barrow, where we were traveling in 2 days to 5 different venues. And that you might remember Deward explaining that he had been looking for many decades for an answer. And the hang, he talked about, you could stand on the stage and touch the bottom of the line array. The whole idea behind that is that in a 1 meter box down to approximately 500 hertz in one single LVH cabinet, you get the ability to control the directivity in such a way that you can put out a 4-to-1 type of ratio emulating what used to be done in a 9-box or a 6-box or a 7-box, depending on the application, line array.
Yeah, I mean, one of the things we didn't get into really was that, a single LVH box can control the vertical pattern down to about 400 hertz. And to do the same thing with our IV6, it takes 4 to 5 of those boxes to control down to 400 hertz. So again, from a sightlines perspective, one LVH takes the place of 4 or 5 IV6 boxes, but both in coverage and in pattern control for reverberant spaces.
And the LVH is combined vertically. So in Charlie's video, he showed a pretty significant vertical line of LVHs. So that was controlling pretty low. Pattern control pretty low.
Mm-hmm. Correct.
Cool.
Yeah, those were in that scoreboard system, the video. Those are 3 LVH devices treated as a single loudspeaker.
So 3 meters tall.
Correct.
Yes.
9
Give me
feet.
the math on that. Yeah.
9
As
feet
soon as
plus.
we get into 2 cabinets, now you have the opportunity to go lower in pattern control because the wavelength with those additional 12-inch drivers gives that ability.
Yeah, cool. Thank you. Thanks for clarifying that.
Thanks for paying so much attention and remembering a slide from like 3 hours ago.
Well, yeah, I mean, it's kind of interesting because here I am showing, all these boxes and how we sucked that up into a 3-meter box to get that kind of performance. And then later we come back and show how you can array that 3-meter box. So it is a bit of a challenge to communicate all of that clearly.
It's a complex question that you're solving.
Sound reinforcement guy. So.
Thank you. Nice job, you guys.
Thank you.
I'd like to take a moment to really thank the people that are 3 hours ahead of us, which is most of the presenters, and then Deward, who's 1 hour ahead of us. Thank you for staying up late to do this. We really, us people on this coast, really appreciate it.
Absolutely.
Well, thank you all for having us. It was a pleasure to put together and enjoyed presenting it to you guys.
Well,
Yeah,
please,
thank you very much.
yeah, please feel free to join us anytime too. Keep tabs. You're always welcome at our meetings and hope to see you again. Yes.
I was a little bit worried because I attended the session last month with JJ, and that's a hard act to follow.
He is a treasure. You guys are treasures too. This was cool.
What did JJ talk about last month?
That video is up, I think.
Oh, I missed that.
Jess will tell you.
Basically, the mechanism of hearing.
Yeah, the title was Audio Signals versus the Ear, Time, Frequency, and Bandwidth Revisited.
Yeah, really interesting, as usual.
Great talk.
Yeah. Yeah, I appreciate anything that JJ puts out. Yeah, we worked together on the MPEG committee back in the day. That's how I know him.
Cool.
Sounds like this is the chapter to be hanging out with, huh?
It is.
Get me on the mailing list.
You can sign up. Do we have our... Did you see our webpage? You probably didn't. You got the link independently.
I think so. Yeah.
Let me drop it in the chat.
Yeah. Yeah. Hang on long enough to get that from Jess.
All right, folks, we're going to start migrating around the room and not looking at videos and computers anymore.
Sounds good. Yes. Time
Thanks,
to
you guys.
decompress.
Take
Thank
care.
you.
Thank you.
Yes.
Yeah.
Thank you.
Yeah.
Yeah.
You'll want to mute us in the room there.
Already did.
Okay.